I'm sorry, the difference between different types of links and the different implications that using one link versus the other could have in your analysis results. So hopefully by the end of this webinar, you'll have a little bit more information about links, and it will help you have a more informed decision as to what link to use. Before I jump into the content of the presentation, just wanted to give you a little bit of background about myself. So I did my bachelor's degree in civil engineering at the University of Puerto Rico. Then I moved to Connecticut to do my master's and PhD at the University of Connecticut. And for the past 5 years, I have been working at GM2 Associates as a structural engineer. I consider myself lucky in the sense that I have been able to work in a wide variety of projects at GM2, both from the design aspect as well as from the load rating side. A few of the key projects I have worked on, for example, this one here is a superstructure replacement we did in Providence, Rhode Island, a very fast-paced design build project. It was done in 6 stages, and each stage was about a week. So very fast-paced, very challenging and interesting project. I was also involved in the design of the full structure replacement of this bridge over I-91 in Connecticut. We end up using a GRS IBS abutments, which is a type of abutment developed by FHWA, and it ended up working very well for this structure. From the load rating side, I have been involved in numerous load ratings over the past few years. I think at this point probably lost count of them. The most prominent, I would say, it's the load rating of the Gold Star Bridge in Connecticut. For those of you who are not familiar, the Gold Star is one of the iconic bridges in Connecticut, actually considered the biggest bridge in the state. So again, very lucky to have been able to put my hands on this bridge. As far as the presentation, I'll start with a brief introduction of links, why we need them, and where are they used. Then I'll proceed to discuss the different types of links. I'll touch a little bit on elastic links versus rigid links. What's the difference between those two? I'll talk a little bit about the different types of elastic links and the different applications for those types. Then I'll talk a little bit about model validation, which is, in my opinion, one of the most important part of the presentation. I'll present a few validation examples and a few workarounds for the most typical issues that we normally see. And then I'll finalize with some modeling considerations and tips for when you are modeling links in Midas. I want to start with presenting the concept of insertion point because it's something that's going to become more and more relevant as we go through the presentation. So when you have a beam element on an FEA model, basically, obviously, you're going to have that element is connecting 2 nodes, right? So those nodes represent a point within the cross section. By default, in Midas, that reference point or that insertion point, it's at the CG of the section. So for those of you who have done a lot of models in Midas, you'll probably notice that most of the times we end up having to move that insertion point somewhere else in the cross section. So in that case, that's what we call an offset insertion point. And again, it's something that it's used in most models in bridges. So keep that in mind as we go through the presentation, because I'm gonna be referring to the insertion point in a few different occasions. So here we have a typical steel girder superstructure. And if we look at it the way it will look on a Midas model, essentially we're going to have beam elements for the main girders, and you're also going to have the elements and nodes for the cross-frame members. Now, these cross-frame member elements are at a different elevation from the girder nodes, from the girder elements. So at this point, the software doesn't know that they are connected, right? In reality, physically, we have a connection plate and we have a web that is connecting the cross-frame to the girder. At this point, the software just doesn't know that. So that's why we have to tell the software that these are connected. These are physically connected, and that's what we need links for. For example, here it's a cross section of that same bridge. Again, here at the top, we have the insertion point of this plate girder, and then we have the cross-frame members. So even though if you turn on the 3D rendering in Midas, it will look like these nodes are touching that plate girder. But again, at this point in reality, the software doesn't know that they are actually connected. So it's not until we bring the links in that we tell the software that these are actually connected. So this is one of the simplest applications of links, and it only gets more complex from there. For example, you could have a more complex structure where you have stringers that are resting on floor beams connected to a truss. And the cross section of that will look something like that. So you have your deck supported on your stringers that are in fact being supported by the floor beams connected to that main truss. So in the model, it will probably look something like that. This being the insertion point of the stringers, insertion point of the floor beams, and then your main truss element. Again, at this point, we have to tell the software that this, all of these elements are interconnected. That again, it's done with links. So now that we have a good understanding of where we apply links on, why do we need them? We can jump into the types of links. Essentially, there are two main types of links. You have elastic links and you have rigid links. Briefly, elastic links behave similar to an element in the sense that they have a stiffness in the different degrees of freedom. Rigid links, on the other hand, it's either you have the degree of freedom released or you have it rigid, right? So the rigid links are more of a displacement constraint, whereas the elastic links, you have a stiffness that the user has to define to that link. And I'll get a little bit deeper into the differences between the two a little bit later. So as far as elastic links go, you have different types. You could have a rigid elastic link, compression or tension only link. You could have a general link or multilinear. I want to make the distinction that rigid elastic link, it's not to be confused with rigid link. In some applications, you may use one or the other and end up getting the same results depending on the application. But the way the formulation works and the way the software looks at it, it's completely different. So like I said, elastic link act similar to an element. So in that sense, you can only connect two nodes with an elastic link. So you're going to have two nodes, and instead of having an element connecting those two nodes, you're going to have an elastic link with the stiffness that you assign to that link. And let me, right, so jumping up to the first type of elastic link I want to discuss, probably the most commonly used elastic link, it's the rigid elastic link. And basically what you have here is a link that has infinite stiffness, or is simulated to have infinite stiffness in all 6 degrees of freedom. So when you select an elastic link, a rigid elastic link in Midas, it will automatically assign a very high stiffness to simulate rigid behavior. And when I mention very high stiffness, it's really a very high stiffness relative to the elements that are surrounding that link. Typical uses for these links include near at the ends of plate girders, where you link the support node to the node at the bottom of the girder. Later, I'll have a little bit more detailed discussion on the end conditions. And then we also use that at diaphragm connections. So when you have a channel diaphragm or double or wide flange section used as a diaphragm, we typically use a rigid elastic link to connect that to the girder. The other type of elastic link, it's a compression or tension only link. So this type of link is only going to have axial stiffness, depending on whether it's compression only or tension only, and then it's going to be active only in one or the other. These are typically used when you have special configurations or solid structure interaction. For example, when you have integral abutments, it's very common to use compression only links. Something very important to know about these types of links is that they are nonlinear in nature. And the reason for that is it requires an iterative procedure to be able to solve a structure when you have these links. So to understand that, I just wanted to briefly mention how these links work and how the software looks at it. So let's say you have, for example, a structure where you have compression only links. As an initial guess, the software is going to consider that all of those links are active. Okay, so it is going to analyze the structure, assuming that all of those links are active, and it is going to find out which of those links are in compression and which of those are in tension. Those links that are initially found to be in tension will be removed from the model automatically by the software. They will be removed from the model, and the software will rerun the analysis. So it's going to keep doing that iterative procedure until it finds that all the links, all the remaining links are in compression. So having that in mind and knowing the inherent linear nature of the influence lines used for moving load analysis, these links cannot be used for moving load analysis. So if you need to do a moving load or a live load analysis for a structure where you have these links, essentially you're going to have to come up with different locations of the truck that you want to investigate and have that as a static load, and then run the analysis based on that static load or series of static load cases to be able to capture the governing effects. The other type of link is a general link. general elastic link, and as the name suggests, this is the elastic link that gives you the most flexibility in the sense that you have to define a stiffness in all 6 degrees of freedom. Now, that stiffness could be a known value, or it could be a very high stiffness to simulate uh, rigid behavior uh, in some of the degrees of freedom. So, for example, uh, an area where we have used these types of links is this truss bridge where we have the stringers connected to the floor beam. On this image, basically, this stringer on the right, it has a fixed support on the floor beam. The one on the left has an expansion support on the floor beams. So for the one with the expansion support, we define this link here as a general elastic link. And all degrees of freedom except for the axial degree of freedom, all the degrees of freedom, we wanted them to be rigid. So we had a very high stiffness to simulate rigid behavior, and then the axial stiffness, we set that to 0. So we could get that expansion at the support of the stringer. So I mentioned that we use a very high stiffness to simulate rigid behavior. Now that's something that you need to keep in mind for general elastic link. If you're going to do that, you have to make sure that you calibrate that stiffness that you're using for the rigid behavior. And there's a very straightforward process to do that. Uh, Basically, you want to make sure that whatever high stiffness that you're using, it's actually simulating that rigid behavior that you want. So the process to calibrate that stiffness is you can create the model with all the links modeled as rigid elastic links, and then create a duplicate model, and the location of those links where you need to release one or more degree of freedom, change that to general elastic link at those locations. But then use a high stiffness in all degrees of freedom, right? So essentially, where I'm going with this is you want to have one model with rigid elastic links and a second model with general links that have a very high stiffness that behaves exactly as your first model. So it may take a few iterations, but you want to make sure that you increase that stiffness in the general elastic link until you get the same results as the model with the rigid elastic links. At that point, then once you get the same results between both models, at that point, then you can say that the high stiffness that you have assumed or calibrated, it's actually behaving as a rigid behavior or as a rigid link. So after that, then you can start releasing or applying the known stiffness to the specific degrees of freedom that you need to do. In our previous case, after we did this, we got the same result from both models. Then we just released or we assign a 0 stiffness to the axial degree of freedom. Now, moving on to rigid links. As I mentioned before, rigid links, it's more of a geometric constraint. So what it does is it keeps the distance between the nodes that are being constrained, keeps that constant throughout the analysis. And another main difference between rigid links and elastic links, it's that with rigid links you can link more than 2 nodes. So the way it works is you have to define a master node, then you define one or more slave nodes. And again, the distance between those two are kept constant throughout the analysis. So what happens is, if your master node experiences some translation, that slave node is going to experience the same translation. If your master node is experiencing rotation, then that slave node is going to experience translation and rotation. So that slave node essentially can move due to translation of the master node, due to rotation of the master node, or a combination of both. Another thing that's very important about these types of links is that the slave node is going to pick up all the properties of your master node. Right? So if you have a support condition of your master node, essentially that will get transferred to your slave node, and we'll talk about that in a couple of slides. So typical applications where we have used rigid links, add beam elements to plate elements transition. For example, here we had a bridge, a top girder bridge, where we modeled that with beam elements, and the analysis with beam elements suggested that the bottom flange was buckling. The capacity of the bottom flange was insufficient, and it was buckling because of that negative moment that it was receiving, or compression on the bottom flange rather, due to that negative moment. So we wanted to investigate further whether that bottom flange was actually buckling. So we already had the beam element model. So we created the top girder with plate elements within the region of interest, and then used rigid links at the transition from beam to plate elements. In that case, we used the girder node as the master node, and then the nodes along the perimeter of the top girder as our slave nodes. Perhaps the most typical application of rigid links is at the ends of the girder when you are modeling your support conditions. So I wanted to show here 3 different configurations that I have seen when looking at different models, 2 of which are not correct, and then the last one here, it's the correct configuration. So the first configuration that I have seen is you have this node here is the insertion point of your plate girder, and then you have the node for the cross frame and a node at the bottom of the girder. So I have seen that that insertion point gets assigned as the master node, and then all of these 3 nodes are slave nodes. Now the problem with this is what I mentioned before, that the slave nodes are going to pick up the properties of the master node. What happens is your master node here doesn't have any support condition. So that means that these 3 slave nodes are going to pick up these properties. So that means even though you have a support condition defined here, once you start running the analysis, this node will pick up essentially that. So this support condition is going to be deleted from the model. Luckily, Midas gives you a warning for that. So it's going to tell you that the constrained degrees of freedom at the slave nodes are automatically released. So you may get this message and may not be aware why is that happening. It's because you have a support node as a slave node. So that is essentially getting deleted when you start the analysis. And in that case, again, if all your supports end up being removed during the analysis, then your model is just not going to run. So the good thing is that's something very easy to pick up. The second case is similar configuration, but the support node gets assigned as the master node. Now, this one is a little bit more trickier to catch because the model it's still stable with that, and it's going to run, and unless you know it's not correct, you won't be able to see it right away. Again, and the problem with this configuration is that your slave nodes are going to pick up the properties of your master node. So that means that this support condition that you have here is essentially going to be applied at each of these nodes, which is obviously not what we want. So the correct configuration is to have an additional node below that bottom of the girder node, and that's the one that's gonna be assigned as your support node. Then you can use an elastic link between these two nodes. So essentially, you are isolating that support condition from your master node. So after knowing what we know about links, the most important piece of advice that I can give is validation. You have to validate your model because you may have a link defined the correct way in the sense that the structure is stable and everything, but it still may not be behaving the way it's intended to do it. So as far as the approach for applying links, I think it's very useful to start with a very constrained model and then start releasing the degrees of freedom gradually. What that's gonna do is, for example, you start with a very constrained model and you validate the structural behavior of that model. You run the analysis, everything looks good. Then you start gradually releasing the degrees of freedom of the links that you need to release. And along the way, as you're releasing them, you run the analysis and make sure that everything is going the way you want it to be. That way, if you at some point you reach an instability issue, you will know exactly what release is causing that instability, as opposed to starting with a model that has all the releases you need. It ends up being unstable, or it ends up not behaving the way you want to behave. Then it's a lot more difficult to figure out what is exactly causing the issue. Typical items we use to validate, very straightforward to look at bending moments. If you have a simple span, or if you have a continuous span, you know what those bending moments diagram should look like. So it's very easy to just look at that and qualitatively see whether your model it's doing the right thing or not. Same thing with deflections. If you have look at the deflected shape, see if it makes sense. Look at the actual values of deflection that you're getting. If you have a 100-foot sample span bridge, and you look at the deflected shape looks good, but then you look at the values and you have like 10 inches of deflection. Obviously, there's something wrong with that. Unless you look at those things and validate that, there's no easy way of knowing whether there's something wrong with the model or not. Another item or tool for validation, it's verifying the intended load path. So if you, by judgment, you know that if you apply a load at one point, it should get, that should get transferred into next moment this other element. So you apply that in the model, see whether that behaves that way. Same thing with, you could do that at different locations in the model with different member forces, and see whether the member forces you're getting in the model are actually what you should be expecting. So the first validation example we wanted to talk about, it's a simply supported beam. So what I was telling you about that, you may have the links properly defined, but if you don't validate, you could end up with incorrect results. So this is a perfect example of that scenario. So here I have defined the links at the support the way I explained earlier. But when you look at the moment diagram, you're seeing some negative moments at the end. So obviously this is not what a simple supported beam should look like. So, and again, unless you take your time and look at these, you're not going to see what's wrong with the model. So this has to do with the support or not being at the CG of the section. That will become a little bit more clear in the next example. But once you have this, the workaround or the fix for this, it's really adding beam and releases at the end. So once you add, you keep the links at the end the same way. You add beam and releases at the end. That negative moment is going to drop to 0, and then you end up with the correct bending moment for a simply supported beam. Again, if this is not done, you could be seriously underestimating your positive moment at midpoint, which is obviously something you don't want to be doing. For the second example, here I want to bring back the concept of the insertion point, because like I said, most of the time you'll end up using an offset insertion point. And when you do that, what Midas does internally is that it finds a link between the CG of the section and the offset insertion point. So even though you didn't define a link here, Midas is implicitly assigning a link there. So essentially, you're going to end up with the same issue that I just explained in the validation example 1. So here I have 3 cases. The first one has the insertion point at the CG of the section. And as you can see, without any releases or anything else, you get the correct bending moment diagram for a simply supported beam. The other 2 examples, one has the insertion point at the top, the other one has it at the bottom. So as soon as you have your support or your insertion point anywhere other than the CG of the section, you're going to start seeing these negative moments at the ends. So, like I said, this is a result of that internal rigid link that Midas does when you do the offset insertion point. It is the same issue as the first example. So naturally, the solution is the same as the first example. Once you add beam and releases at the end, all 3 cases will end up giving you the same result. The other validation example I want to bring is this is a truss bridge we were doing, and we checked the model, everything seemed to be fine. When we were looking at member forces, we noticed that forces at the in particular bending moments at the top and bottom chord they just didn't seem they didn't seem right. Specifically this here at the end, we were expecting to have 0 moments at the end, so we were getting these huge moments at the ends of the bottom chord. It took us a while because we thought we had the model properly defined and everything. After looking at it for a while, we noticed that out of all the members of the truss, these 2 diagonals had the insertion point at the top instead of the center. And because of that, that was essentially causing the whole structure to behave improperly. So once we notice that, we change that insertion point of those two diagonals to the center, and immediately we end up getting a much more intuitive member forces. So here I'm just showing the difference in member forces from one model versus the other one. And not only we had a huge difference in the shape of the moment diagrams, but if you take a look at the values of those member forces, for the first model, we were essentially getting 7 times more positive moment than the second model, obviously at a different location as well. So again, simple things in the model, simple inputs in the model that can hugely impact the results of your analysis. The other example is again that same truss bridge. We have the stringer the stringers that are supported on the floor beams. So for those we use rigid links. And those rigid links initially we had all degrees of freedom constraint. And when we looked at the moment diagrams of the stringers, we noticed that there was something wrong. So these stringers are continuous over the floor beam. So we were expecting typical positive moments between floor beams, and then seeing that big negative moment at the floor beam locations. But when we looked at the bending diagrams, we did see that negative moment at the floor beam locations, but immediately at the other side of that floor beam, we were seeing a positive moment. So there was a step in the moment diagram that it was just not making sense. So that immediately raised a red flag that there was something going on with the model. And after looking at it for a while, we finally figured that the rotation of this master node was introducing an additional moment on that stringer, and that was causing the issue. So what we did to fix it is we kept the link as it was, but we just released the moment in the y-axis, and just by doing that release, we were able to get the moment diagram that we were expecting. So you'll see your peak negative moments at the floor beam locations, and then a positive moment between the floor beams. So again, just comparing the huge difference, something as simple as one release in a rigid link can have in the result of your model. The last example I wanted to bring for as a validation example, it's a kind of an unusual bridge configuration that we had. So this is a girder floor beam system with a very high skew. We have the piers along these lines. Then these are our screw girders. Traffic is going in this direction, northbound and southbound. And then these are our floor beams. So the most unusual configuration of this bridge is that we have a diagonal joint running along one of the floor beams. So this bridge, when it was designed years ago, it was designed so that the left side of that joint expands this way, and the right side of that joint expands this way. So basically, these are all fixed bearings, and then to the right side of the joints, they become expansion bearings. Then the opposite happens on this side. You have fixed bearings on this side and expansion bearings on that side. So the original joint detail was like this. So it has the left side, it's attached to that floor beam, so it's fixed, and then the right side of that joint, to the right side of that joint, the deck was free to slide over that floor beam to obviously allow for the expansion of the bridge. The problem with that is that with time, not only that floor beam began to corrode because of leakage through the joint, but this side of the deck ended up hammering against the top flange and damaging the deck. So we were doing the rehabilitation of this bridge, and as part of the rehab, we wanted to come up with a tie down system that restrain, prevents that deck from hitting the top flange while still allowing for the expansion that needs to occur for the bridge to work. So for that, we needed to do two things. First of all, we need to know why the deck is hitting against that floor beam, what's causing that scenario, and after that, we have to come up with a design load for this tie down system. So we looked at it, and essentially we found two configurations that were causing that deck to hammer against the floor beam. The first one is when you have your trucks loaded this way. Essentially, each half of the bridge is deflecting like that, causing that side of the bridge that is not attached to the floor beam, it's causing that side to open up. So once this load is removed, obviously this gap closes and it hits the top of that floor beam. The other more intuitive scenario where that happens, it's when all your trucks are loaded to one side of the joint. So the side of the joint that is fixed, or the side of the deck that is fixed, will deflect with the floor beam, and the side of the deck that is not attached to the floor beam essentially stays where it is. So picture your trucks going from the left side to the right side. So you're gonna have this scenario, and then immediately after that, you will unload this side. So it's gonna go up, and you will load this side, which will cause it to go down. So that was the other scenario where the deck was hammering against that floor beam. So in the Midas model, we had it modeled that way. So essentially, this is the fixed side. That's the side that was free to slide over the deck, and we use a series of elastic links to model that, and essentially use the force on those links to come up with the design load for the tie down system. And the last part of the presentation is the modeling considerations and tips. So how do you begin to think about what type of link you should be using in your structure? First thing you need to consider is what degrees of freedom you need to constrain. If you need all degrees of freedom constrained, then you could use a rigid link, right? Either rigid link or a rigid elastic link, depending on whether you need member forces or not, or depending on your application. If you know that, if you know the stiffness in one or more degree of freedom, then you may need to go with a general elastic link. If you have a special configuration, then you may go with a compression or tension only link. You should also consider the size of the model. For smaller models, it's not really that big of a deal. But as you model larger and larger, or as you build larger models, it's going to become more important because, like I mentioned, elastic links are essentially elements. So that means that they will go into stiffness matrix, and the software is going to come up with member forces for those elastic links, which is not the case for rigid links. So that means the influence lines and the moving load analysis, all of that um, influence of the moving load have to be calculated for elastic links. So larger models, elastic links tend to take more time to solve. The other thing you want to consider is whether you need member forces at the location of the link or not. Whether it's a special configuration like the tie-down system that we had, or you have a beam where you need the reactions because you're doing beam trading. If that's the case, then you're essentially going with an elastic link, which is the link that will give you member forces. And the last model in consideration is validation. No matter what you're doing, whether it's looking at links, beam and releases, or a simple model, you have to validate it because it's very easy to have a model that looks right from the model's perspective, but it behaves the wrong way, or it does not give you the result for the information that you're targeting to obtain. The final model in consideration I wanted to bring is link management. This is not something that needs to be done, but I think I have found it very helpful. And again, when dealing with larger models, Midas has boundary groups, so you can assign links to those boundary groups. And what helps a lot is to name those boundary groups or those links with something that is descriptive of what they are connecting. Well, for example, here we have stringers, rigid links. I know that all the links assigned to this are rigid links, and they are connecting stringers. So that again, it's not technically needed, but that becomes more important when you are, first of all, self-checking your model. If you have a very large model with a lot of links, and you want to check each type of link at a time, you can just, using this boundary group, you can only turn on certain links to help you isolate that. And it will also help if somebody else is using the model, whether it's checking it or taking it to further completion. It's going to make it a lot easier for them to check that model and to make sure that everything is fine properly. So with that, that's the end of my presentation. I'll be happy to answer any questions you guys may have. Thank you.
All right. Thank you so much, Luis. So yeah, we do have a bunch of questions. And before that, I just want to thank you, Luis, for this wonderful presentation. Just a very slotted model with very in-detailed link applications. We're just very impressed. So I can go ahead and present some of the question right now. Just give me 1 second.
Okay, so let's to find big value, define the insertion point to anything but center. You find out by doing so. Starting the insertion point, it seems to be line bracket value. Short answer is yes, I do. I do see value of defining the insertion point, other than center. I know it may look like it's just like for graphical purposes, but Again, it's when you have larger models, it really becomes if you don't have things graphically correct, it really becomes very easy to have omissions or to miss something that that may be affecting the model. And there's no need to be to move away from using offset insertion point as long as you take the proper precautions and validate your model. I think the benefits are really there. Let's see. Links for binge bearing and bearing to substrate connections. How to accurately model different bearing types. That's a very good question. A way of defining, for example, elastomeric bearings, you can have a support node and the elastic link that you use to connect the bottom of the girder node to that support node. You could make that you could assign the stiffness of the elastomeric pad if you want to make it more accurate. Another way of doing that is you can have that link from the bottom of the girder to the support node. You can have that as a rigid elastic link, and then the support use instead of defining the typical support, you could define that as a spring support. And again, in that case, the spring support you have to define the stiffness for it, so you can define the stiffness of the elastomeric pad uh, uh, on the spring support. And bridge flow rating design using Midas Civil versus Leap RC here. Um, I don't have any experience with Leap load rating, so I can't speak to that. About the Midas, I think Midas has a very robust load rating module, especially uh, for pre-stressed concrete and for steel composite girders. I think it does a very good job of doing the load rating. What I would recommend though is, again, it comes back to validation. Um, when you're doing load rating, for example, in Midas, it's worthwhile checking that everything has been entered properly. So you could check, just do spot checks of touching properties. Make sure that, for example, for a composite girder, it's taken the correct stiffness, second properties at the correct stages. And also you could spot check capacities and rating factors calculation, just again, just to be on the safe side and make sure that you are covering your bases and you're doing your due diligence uh, when using the software.
All right. I think our time is it's up, unfortunately. So if you do have any other questions, which I do see some other questions, we would definitely try to answer it via email. And then again, I want to say that this webinar is recorded, and we'll send you a follow-up email containing the link with the presentation PDF file. So you're gonna find it on our website. Yeah, and then just in case you have missed it initially, this webinar is provided by Midas expert Luis, and like a lot of other experts, Luis is really good at Midas, and if you do want to connect more with experts like Luis, you can join our Midas expert network, and it's totally free because we want to have a better interaction between users and between us and users, of course. So yeah. So Luis, do you have any closing notes that you want to say to the audience?
No, other than thank you for joining us today, and I believe we do have a smaller Q&A session now, right? So
Yes.
if you sign up for that, I'll be happy to answer any additional questions that.
All right, great. So I think the post-webinar discussion session, we can take a probably 5 minutes break. So yeah, for other than that, I think really appreciate everyone to show up, and I hope you learned a thing or two today. And so yeah, we'll close it from here. I hope everyone have a good day, and please stay safe and stay healthy.